Welcome to 6502 Assembly Language Programming. In this video, we'll look at writing an integer divide routine for the 6502. This is a relatively advanced topic, and it will help you to be familiar with 6502 load, store, shift, rotate, increment, and conditional branch instructions. Shift and rotate instructions are particularly important, so I'm providing links to those videos. We've already learned that the 6502 does not feature a multiply instruction. Well, it doesn't have a divide instruction either. So if your program needs division, you'll have to do it in code. Let's consider the algorithm used for ordinary decimal division. We begin by trying to divide the divisor by the first digit of the dividend, which is 1 here. Now, 5 obviously does not divide into 1, so we then go to the next digit, forming the number 12. And 5 goes twice into the number 12, so you write 2 up there, multiply that back, we get 10, and then we subtract that to get a remainder of 2 from that operation. 2 is smaller than 5, so once again we add a digit and try that division operation. We get an answer of 5 from that, so we multiply that back to get 25. We do the subtraction and we have 0 as our remainder. The algorithm for binary division is similar to that of decimal, except that the divisor will go into each partial dividend either 1 time or 0 times. So then the algorithm doesn't require any division operations, which is quite handy for us because of the 6502's lack of a division instruction. As with decimal division, we will start at the left of the dividend and try to form a number that is greater than or equal to the divisor. As we add digits, we will add a 0 to the quotient if the number is less than the divisor, and a 1 to the quotient if the number is greater than or equal to the divisor. In the assembly language implementation, we will accomplish this process of adding digits to a partial dividend by shifting bits into a variable representing that partial dividend. We'll also be shifting bits into a variable representing the quotient. So we'll keep adding digits until we have a large enough value. So here we have formed the value 6, represented by this binary string that is larger than 5, and so we can put a 1 into the quotient instead of a 0, and we can subtract the divisor from our partial dividend, giving a remainder of 1. Once again, we've accumulated a value, or assembled a value that is equal to or greater than our divisor, the value being our partial dividend. And so we'll write a 1 into the quotient. We'll subtract our divisor, and then we'll have our remainder. The remainder is 0, and we're out of digits, so this is the answer to our problem, and we have a remainder of 0. Now we'll look into a binary division algorithm in 6502 assembler. I've set up this virtual computer to illustrate the operation of our algorithm. The big white arrow represents the program counter. The table shows our variables and the relevant registers. It'll be updated as we step through the algorithm. Quotient is where we'll put our answer. We also use it for temporary storage of the dividend. This allows us to use a single instruction to shift the bits of the quotient into it and also shift the bits of the dividend out of it into partial div. Partial div is where we build our partial dividend. Shifting bits into this variable is how we include more digits in our partial dividend. X and A represent the 6502 registers, and C represents the carry flag. The ASL rotated the high bit of the dividend, now stored in quotient, into the carry flag. The same instruction also shifted a 0 into the low order bit of the quotient. If it turns out that our partial dividend is greater than or equal to the divisor, we'll change this bit to a 1. The ROL rotates partial div to the left and the carry flag into the low order bit of partial div. I'll highlight the bits of the quotient as we build it from the low order bit of the variable quotient. We've now added a second 0 bit to the quotient, and we'll keep adding zeros until partial div is equal to or greater than the divisor. Partial div is finally equal to or greater than the divisor. So we'll change that last bit we added to quotient to a 1. We'll also subtract the divisor from the partial dividend and update it as we did in the manual procedure. Once again, partial div is greater than or equal to the divisor. So we're going to change the most recently added bit in quotient to a 1 and also subtract the divisor from partial div. Okay, so we're out of digits and our remainder is 0. The remainder would be the value that's in partial div. It is 0. So we are done. And our answer is 5. Here it is in quotient. Oh, pardon me, let me get my red pointer. Here is the answer in quotient. Our answer is 5, and our remainder is 0. So let's go check this out in the IDE, and you'll have a chance to code your own solution to a divide problem. You'll find these links in the description below, and you can click on one of them to get to the course source code and solve the exercise. Welcome to the 8 bits in 1 byte website. Let's navigate to the course source code. We'll click on Learn 6502. We'll click on Course Source Files. And since I've been saving my work as I've gone along, the website sees that and gives me this link to click on. Now if we run this code, we'll see that I've solved almost all the exercises. I only have this one exercise left to do. So let's get into that. If we look at EX11, ASM, we can check out the tasks that we have to solve. So it says divide the 8-bit dividend in param 0 by the divisor in param 1, putting the answer in output 0. Now this should be fairly easy for you because I've given you the exact algorithm that you need in the first part of this video. So feel free to pause me now and code your own solution. Welcome back. So let's go ahead and load my solution. Now, there's a couple of things I want to point out here. One is that I have a bug here at the bottom where I forgot to put my pound sign in front of implemented. Somehow the code still works, but I do want to fix that. So I'll do that now. Also, my variable names here are not very good. Instead of using quotient and partial div, I use inward 0 and inward 1. So I think I would like to fix that. So I'm going to use code mirror to do that. I'm going to replace inward 0 with quotient. Oh, that didn't work. Okay. Well, no, it did work, but oops. Okay, come on, Rich. Don't go wild. But I do want to change quotient plus 1 to partial div. So we'll do the same sort of thing. I'm pressing Control Shift R, and I'm going to replace quotient 1 with partial div. Okay. So now I have better variable names. However, I do need to define these variables since I have all sorts of references, but I haven't defined them. And we're just going to overlay them, overlay inward 0 and inward 0 plus 1 with these names, with the set directive. So I'll say quotient set inward 0 partial div set inward 0 plus 1, and let's see first of all if that works. Let's run it. Ooh, no errors, and in fact we solved it. Hurrah! So let's go back and walk through the source code here. So we're loading param 0, putting it in quotient, setting partial div to 0, setting up our loop count. This is just like we did in the first part of the video. Here at our loop, we're issuing a wait sync. If that seems confusing, there's a link to an article in the description explaining why. And then we're just going to go through the algorithm that we've already seen. We're shifting the quotient, rolling the top bit into partial div, which puts a 0. This puts a 0 in the 0 bit and low order bit of quotient. And down here, if our partial div is big enough, we're going to issue an inc and set that 0 to a 1. We're going to loop through all the bits in the same way we did earlier, coming up with our quotient that we put in output 0. So there you have it. I won't spend too much time on this since we've already walked through this at length. Thanks very much for watching this video to the end. Please click like and subscribe if you've derived any benefit, and you have a great day.